Here's some discussion on homework problem number 12. Homework problem number 12 refers to two charged rings that sort of face each other 20 centimeters apart, and it gives you some charge that appears on each ring. It looks like they're oppositely charged. One of the rings is positive, one of the rings is negative. In order to do a problem like this, you have to just drop back and think about a result we got in class, which is, what is the electric field outside of a single ring? So here I have sort of indicated, here's a ring here, and suppose this ring is charged here. Could be positive or negative charge. In either case, there's a charge Q, which has been spread on this whole ring here. And we know from class that there will be an electric field that exists a distance from this ring. And the only case we can sort of handle in this class is the electric field all along the z-axis. And what we know is that there will be an electric field pointing this way, EZ, at some point at distance z from the ring. That's what we know. And we have a formula for that as well. It turns out the magnitude of this electric field, EZ, at this point here, is K times Q. Q is, of course, the amount of charge spread around the ring, times Z, how far away we are away from the charge, times the quantity R squared plus Z squared to the 3/2 power. This is the strength of the electric field at this point. So if you're talking about two charged rings, the way they refer to in this problem, it really just becomes a superposition problem once again. We can have one of the charged rings right here and one of the charged rings right here. And here's sort of a line that maybe connects them geometrically here, although the line doesn't actually exist. This could be the positively charged ring here. This could be the negatively charged ring here. Information from the problem says that the two rings are some distance apart. I'll just call that distance sort of little d, I guess. And they both have the same radii here. We'll call that r, and this distance r as well. And so if you plant yourself at a certain point between the two rings, say at the midpoint, which I think the problem's asking for, say right there, then I know that the distance we are from this ring here would be d over 2, and distance from this ring here would also be d over 2. That's how far we are. That's how far we are away from either ring. So the question becomes then another one of superposition. This point right here has two electric field lines going through it, one because of this ring and one because of this ring. Now we know once again the general rule that electric fields point away from positively charged objects. So there'll be an electric field to this point right here. I'll call that E positive, or the electric field because of the positively charged ring. Because of the negatively charged ring, yeah, there'll be another electric field through this point. We'll call it E negative, pointing towards the negatively charged ring. So you can see that at the midpoint between these two rings here, there's two electric fields, one due to this hoop, one due to this hoop. They're both pointing that way. So really the problem is just an exercise in using this equation. It's a different electric field equation, one for the electric field outside of a charged ring. So we can get that result by saying something like E total. This will be electric field at that point there. Will be KQ times D over 2 over R squared plus D over 2 squared, this whole thing to the 3/2 power. Now where did I get this from? I'm using the general result for the electric field, a distance Z on axis from a charged ring. I'm applying it to the specific case of a distance D over 2 from this positively charged ring. Q is the amount of charge on it. I'm a distance D over 2 away from it, and I have everything filled in just like that. Now there's another electric field, of course, due to the negatively charged ring, so I'm going to add that result in here as well. So I can just put a big plus sign right here and do K. I'm also a distance D over 2 from the negatively charged ring over a similar denominator, R squared plus a D over 2, that quantity squared, all that to the 3/2 power. This is an R, this is a D right here, and this is a 2. So this, in a nutshell, once again, is the answer to this particular problem. Now you can proceed and start plugging in numbers on your own, but I will caution you once again, we've assigned the sign convention on these electric fields in this figure right here. They both point towards the right. Now granted, this is due to the positively charged ring, and it tells you that this Q here should be positive 20 nanocoulombs. And this is a negatively charged ring, which you would think would be negative 20 nanocoulombs. And you're right, there are negative 20 nanocoulombs placed on this ring right here. But if we put a negative 20 in further here, it's going to say mathematically that this electric field points the other way, which won't be right. So I'm also going to put a positive 20 nanocoulombs in for this Q, even though it's a negatively charged ring, because I need its electric field to point that way towards the ring. I don't want to mess with this positive sign, which I've set due to my sign convention. And that, in a nutshell, is the problem then. And hopefully in part B, when I ask you what the force is on a charge placed at the center. So now there's no charge right here, but if I just sort of came in part B of the problem here and put a 1 nanocoulomb charge right here, so I put a little charge here, which had a Q of the charge here of 1 nanocoulomb, hopefully you'll know that if there's an electric field here now, which is given by E total, then the force this 1 nanocoulomb charge is going to feel is always given by Q times E total right there. So the total force it'll feel is going to be the 1 nanocoulomb times ET, where of course ET is the total electric field that you found at that point.